check this out. We've got something really fun today. This is so amazing, man. Oh man, again? 7.2, transformations on exponential functions. Here's how the transformations would look on an exponential function. A is our vertical stretch and reflection. C is the function itself, so we cannot change that. Otherwise, we'll be creating something entirely new. B is 1 over our horizontal stretch, and it's also our horizontal reflection. H is our horizontal translation, and K our vertical translation. We want to transform 4 to the power of x into 4 to the power of negative 2, x plus 5 minus 3, and sketch it. Let's use mapping notation to find the points on the new graph. So what happened to x? Well, it was reflected and also stretched by a factor of 1/2. So we'll say negative x over 2. Then it was moved left 5 units, so we'll say minus 5. All that happened to the y's is that we moved it down 3 units, so that would be y minus 3 for our mapping notation. In order to find the points on the new graph, we need the points on the old graphs, and we're not given that, so we'll need to find those points. We could just make a table directly from this, but we want to transform this graph here. Let's try that. Negative 2, put in negative 2 here, and we get 1/16. Put in negative 1, and we get 1/4. Put in 0, and we get 1. Put in 1, we get 4, we get 16, 64, and 256. And that's why we can't see it after x equals 2, because it's gone too far. All right, so let's take each x value and each y value and find out where they went. So this one becomes negative 4, negative 4.5, negative 5, negative 5.5, negative 6, negative 6.5. You see the pattern. And the y's, they become just approximately negative, because I'm just going to graph it here, so that's about as accurate as I can be. Negative 2.9, negative 2.75, negative 2, 1, 13, 61, and 253. See if we can plot those. Obviously, these two will be too high, but we can plot this one here, negative 6 and 13. Negative 5.5 and 1. Negative 5 and negative 2. Negative 4.5 and negative 2.75. And negative 4 and negative 2.9. And there we go. So we know it looks like this. This goes very high here. Let's see if we can draw at least this much of the graph. Now, all exponential functions have horizontal asymptotes. So we can see that this horizontal asymptote before anything happened was at y equals 0. And if we move the whole thing down 3 units, our new horizontal asymptote will be at y equals negative 3. And that will just help us draw the rest of the graph. We see that we're getting very close to it, and we don't want to look like we're touching it, so you just got to exaggerate the distance there. Almost looks like we're going flat, or maybe even the wrong way. There. And there we go. And this is our new graph of 4 to the power of negative 2, x plus 5 minus 3. And our asymptote, just for fun here, is y equals negative 3. A cup of water is heated to 100 degrees Celsius and then allowed to cool in a room with an ambient air temperature of 20 degrees Celsius. The temperature T is measured every minute, and it's found that the water cools 25% every 5 minutes. not 25% of its total temperature, but 25% of its total temperature change. So if you look here, we were at 100, and after 5 minutes, which would be right there, we've lost 20 degrees. So you can see that 20 degrees is not 25% of 100, but it is 25% of the total temperature change, because we see here that the cup of water is going to cool down and get closer and closer to room temperature. It's not going to continue to drop and go all the way to 0 for no reason. So after 5 minutes, we've lost 20% of the total temperature change, and the total temperature change is 80. So 25% of 80 degrees is 20 degrees, so we've lost 20 degrees after 5 minutes. We want to create a function to model this behavior. So temperature, and our variable will be m here, and if you put 100 right here, then you have fallen for the trap, because it's not 100. It's 100 only when there's no other transformations. In this case, there is. See, we've moved our horizontal asymptote up 20. So at the end of this equation is going to be a plus 20. That means that this right here would be the total temperature change, or it would be 80. Because when this part, the rest of this part is 1, then we got 20 plus 80, that gives us our 100 degree y-intercept. Okay, we lose 25%, so that's like a decay rate. So that means we get to keep 75%. Next we have our m, and we want to keep 75% every 5 minutes. So we put a divided by 5 there. Very similar to what we were doing with half-life. There's our equation.
Great job.
We all have some radioactive material in our homes. It usually comes in the form of americium-241. There's about 200 micrograms of that in our smoke detectors, and it has a half-life of 432 years. It's too bad the smoke detector only lasts 10 years. Anyways, we want to write an equation to model this decay. This one's pretty easy because unlike the last one, we don't have any vertical translation here to worry about. So our starting point here, 200, is our A value. And then we just use our half, and our equation should look something like that. This was part of Relations and Functions 9, Graphing and Analyzing Exponential Functions. Here's some questions. Try them out. See if you know what you're doing.